Welcome. My name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about a G2 gravity standard. I've done some previous videos related to this. One of the very first ones was titled Two Gravities, and it explains in detail exactly how I came to the conclusion that there could be a second gravity. I also had a video talking about what is mass in a theoretical sense. That was question 4 of a series of question videos. And then I talked about the mass of the G1 particle itself, which cannot be in kilograms. And that's part of the reason for these two videos, to explain that point. But let's talk about the G1 standard, which is in kilograms and is the value of mass for objects like the atom, molecule, and larger objects. Smaller objects, G1 gravity doesn't act gravitationally with the nuclei individually, or the electron, or any smaller particles, anything smaller than an atom, and we need a different standard. But there is a standard that's been defined for quite a while. There's several of these around the world, and it has a value of 1 kilogram as measured in the Earth's gravity. It has a precise specification of what it's made of, what its shape and size is, hence its volume. And there is historical precedence for the weight of the kilogram. A long time before it was established, people used the kilogram as a measure of weight, and they knew just about what the weight of 1 kilogram felt like, and the definition of this comes from that history. And we use the kilogram standard weights, and you see this in this picture down here. This is an old chemistry lab scale for measuring objects of atoms. You could, in theory, weigh atoms, molecules, but more likely something larger like sodium chloride. You might put a bunch of sodium chloride here, hoping to get maybe 10 grams of sodium chloride here. You put a 10-gram weight, pick one, a 10 gram, put it here, and you keep adding sodium chloride until the scale balances. This particular old one actually has a preliminary adjustment to account for any irregularities in this, in the way it's made. The whole point is that when this balanced, the amount of gravitational force caused by the Earth at the level of these pans is the same for the sodium chloride and for the standard. The force pushing down on the salt is the same as the force pushing the Earth up. The force on the standard is the same as the force pushing up. And in fact, when it's balanced, these two forces are the same. And the force on the Earth is the sum of the force on the salt plus the force on the standard. That's how we measure it. The whole point being is, if you have a gravitational standard, you measure it in a gravitational field, in this case, the G1 field. And so Newton's gravity equation is a way to determine what that force is. This is the mass of the Earth. This is the mass of the object you're measuring. This is the distance between the two. and the force is in newtons. But you have to know what the value of G is to make this equation work. Well, in 1797 and 1798, Cavendish did an experiment, and this is a drawing of this experiment where he used a torsion force and compared it to the horizontal gravity using Newton's equation. Yeah, I use the term horizontal gravity because that's what he's doing. He's defeated, he is ignoring vertical gravity. He's measuring gravity in the horizontal direction, and the only way you can have that is if there's horizontal forces. Now, people intrinsically think, well, yeah, there's going to be a force between these two objects, just like Newton's equation says. We don't often refer to it as horizontal gravity, but in the particle model, that's important because you have G1 particles moving horizontally back and forth that you're using to do this experiment. What Cavendish did was he knew what the torsion constant K was of this wire. And he knew that if it bent, if this was its neutral position, when the horizontal gravity caused the small mass m to move over here, it would put a torsion force trying to pull it back while the horizontal force of gravity is pulling it this way. And we know that by other science that the torque force on this wire is the constant times the angle theta. That's how it's defined. So you know what that is. If you know the torsion for what wire you have and what the force, the constant is, you take k theta and you compare that to, you make that equal to the force, and then you can do your calculation. So that's the way Cavendish determined the value of the mass of the Earth, by the way. He was looking for the mass of the Earth, and at the same time, he then determined the value of G of Newton's equation. So let's take a look at some equations. This is Newton's gravitational equation. Again, it's an empirical equation that Newton developed not from a theory, but from data. And I've changed it to be a gravity 1 equation. F1 is the force of gravity in terms of level 1 gravity, which is the same as Newton. G1 is what you understand to be the Newton's gravitational constant. M1 is the mass of the Earth, in the case where we've been discussing, in kilograms. This is the mass of the object you're calculating the force from, and it's in kilograms, and the distance is in meters. Now, I mentioned this in another video, and it's Coulombs equation, and we've looked at this equation and said many times, wow, that looks like gravity. And so I redrawn Coulombs equation, said this is the force of the electric field on two charged particles. And there is a constant, this is K also, just like the torsion constant, but this is the constant for Coulombs equation. Coulombs equation is the force in an electric field, or of an electric field. In the particle model, gravity 2 replaces the electric field. There are any number of applications where the G2 force applies in explaining the physics of something, and it is exactly in the same place as the Coulomb's electric force. So I rewrite his equation, and now I have a gravity 2 equation where the force, the gravity 2 force is equal to a new constant, don't know the value, times the mass of something, which I don't have a value for that, I don't have a value for that, but it is an empirical type equation based on Coulombs law. or Coulombs equation. Well, you need two objects, like I've been saying. Cavendish used two small balls and two large balls in his experiments. You have to have two of each to balance it, to hang this thing suspended in air. And the kilogram standard had already been established. He defeated vertical gravity by hanging the small balls in the middle of the rod. Question is, can we do the same thing? Well, number one, there is no historical precedence for the value of this standard. Yes, I'll make sure I'm at the right place. We can make this anything we want. We have to make one. And we can make it anything we want. The magnetic field is the most stable and predictable force caused by G2 gravity. So let's use a large magnet and a small magnet as the two objects for the experiment. Okay, well, you have to define these objects, just like you define the kilogram standard. You're going to make both spheres out of the same material and magnetize them with the same process. Make the volume of the large sphere, that's supposed to be 1,000 times larger than the small volume. Just it's an arbitrary ratio. Later, as maybe work would be done, that would be a different number. Well, we have to make the north and south points. We got to know where they are on the sphere. Where is it? Like we know where the the magnetic north pole is on the Earth. We need to know where the magnetic north pole is and the south pole is on these spheres. And you hang these small spheres on a log rod with a wire that has a known torsion constant. Yes, it's the same setup, and I can use the same picture. Kind of interesting. This is the large magnet, and it's set 180 degrees apart, and it's generally fixed. This is the small magnet, and it's hanging here, and we're going to place for attraction, we're going to place a south pole here and a north pole there, or vice versa. And G2 gravity is going to push these two together. Okay, so here's the general procedure, and I'm not saying this really works. This is just an idea. So we have the large M fixed at 0, 180 degrees. We set the small one at 45 degrees away. I'm not sure what that should be the number. Depends on the magnets and so on, and the wire. And you set it there and you release it, and the attraction, the magnetic attraction, is going to pull on the magnetic ball, and the torsion is going to pull it back because this is a neutral point. And you can now equate the torsion force to the magnetic force and get some kind of answer. Here you can do the repulsion as well. Again, make M fixed. Put the small ball next to the large one. Maybe not. Maybe temporarily you don't have these two balls there because you want to set the torsion force to 0. You want it to be neutral. And so when it's set there, then you bring this one up to that same point. And what's going to happen if this is north and north pole and north pole, it's going to push away and the torsion force is going to pull it back. And again, the torsion constant times the angle is going to give you that force, and you're going to get the force of repulsion. Well, it's kind of interesting that you could do something like that. Now, whether that gets the results you really need, let's talk about that. Well, the units for G1 and G2, the kilogram standard will remain for the G1 gravity. So, but it could be called the G1 kilogram if you really adopted the particle model standard. It's really a standard, and it's the kilogram standard and it's for G1 gravity. The scaling process would be the same. You still have G1 grams, you have G1 micrograms. So you could have really a basic element called G1 gram. The small magnetic sphere would be a G2 gram, and the large sphere a G2 kilogram. That's why I said it was a ratio of 1,000 to 1. So you could say that we have a G2 gram standard or G2 kilogram standard, or both, because you got to define both small and large magnets. Well, things are not that simple. Attraction is G2 gravity pushing the two spheres together, and I just pulled this as magnets now. And so you got, with this, where you have north and south facing each other, and you got G1 particles flowing around and through these magnets. It's really not the flow of the G1 particle that causes attraction. It's really the weakness of the repulsive forces, because right here at this point, and I've done this in a magnetic video I made, and there's a repulsive force that can occur here, and it may be small, but repulsive forces are strong. There may not be many hitting each other right here or here, but it's still there. So the attractive force is not just G2 force pushing it together. It's a combination of pushing force and a repulsive force. And for repulsion is pretty obvious, especially in this case. This is, unfortunately, these arrows are drawn like conventional current and not in the particle model, because in the particle model, the flow of G1 is actually from north to south and around the other way. Particles flow opposite to current. But the diagram shows it nonetheless. When they both are coming out at each other, there's a huge repulsive force because they're hitting directly at one another and they push apart. But they're pushing it. This huge force is pushing against the G2 gravity that's still pushing them together. You can't separate it. They're both there. Well, that's true here. You've got, we measure the net gravitational force here, and we don't normally think of it that way, but in the particle model, you got G1 particles pushing down, and you got G1 particles coming through the Earth pushing up. We don't measure them individually. We don't know what this force is pushing down. We don't know what the force is pushing the Earth up. What we know is the difference, and we accept that. We accept that difference, that supposition. Again, maybe that comes into the picture only because of the explanation for gravity in the particle model. So separating the forces, do we have to do that? We don't do it for gravity 1. Maybe we don't have to do it for gravity 2, and we can still make it a useful equation. We have an empirical equation for gravity 2 based on Coulombs equation. So maybe it's useful anyway. And this method may apply to magnetics, but what about light, electrostatic circuits, and chemistry? I don't know enough yet about G2 mass and how each of the objects, how prisms develop it, how in a Van de Graaff generator it's exactly developed, and in circuits and in chemistry. I've covered all of them, discussed them in general terms, but there's a lot to learn. So are we stuck with this method of magnets or something else like it? Well, there is really a much better solution. It would be best if we could use a G1 particle for the small object and a nucleon for the large object. G2 gravity would cause attraction, and there would be no repulsion. We would be measuring it directly. I admit it, though, I'm not smart enough to know how to do this. I'm not even sure how I could ever even explain how to do this. Maybe someday in the future, if it's ever pursued, someone will figure it out. Well, what's the point of all this? Well, at first, we may learn more about the nuclear binding force. I mean, that's the big one that today. That's where we get all this energy from a hydroelectric, now from a nuclear plant. And we're going to learn more about G2 gravity and how it works. And more knowledge can lead to a better way to use G2 gravity as a cheaper and more efficient energy source. Maybe someday we will gain some benefit from this model. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the particle model using the particle model. Thank you for your attention.